Hello students, welcome to lecture 42 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on hyperbolic metamaterials for super resolution hyperlens imaging. So, we will briefly look into the history and then introduce you to super resolution hyperlens imaging. We will discuss about the physics of the hyperlens and design of spherical hyperlens. So, the history of super resolution hyperlens imaging dates back to the first imaging dates back to 1590. So, that is when optical microscopy invented by Janssen and his son Hans using a tube with lenses. Then in 1609 Galileo enhanced this design with a compound microscope that has got convex and concave lenses, and then in this period Anton could develop lens making techniques, and then he was the first one to observe bacteria, protozoa and blood cells. Now, the conventional optical lenses typically face a diffraction limit. That means the resolution of that imaging is basically restricted to about half the wavelength of the light being used. So, this limit is basically due to sub-wavelength details are being carried by evanescent waves, which could exist only in near field. So, in order to capture those, immersion microscopes were introduced by Abbe that could improve the resolution slightly, and the resolution was enhanced to lambda naught by 2n. Here n is the medium's refractive index, but you cannot make n as high as possible because there is a limited range of the transparent materials. So, overcoming this diffraction limit has remained to be a major focus in the research, where we need to find ways to not lose those sub-wavelength details of a particular object. So, in that query people have continuously developed, and once Professor Sir John Penry predicted the super lens using negative refractive index medium, that could give an idea that how super lens can give you or the perfect lens can give you a perfect image. So, you see air and then you have a slab of negative refractive index material. So, it can perfectly focus the propagating waves. Also, the sub-wavelength feature that is coming from the evanescent waves, which typically decay in a normal medium, they get amplified in this negative refractive index medium, and then after this medium, when it decays back in the image plane, it basically gives you the same amplitude as it was in the object plane. So, you are actually also able to capture the details from the sub-wavelength features, right. So, this was the idea of a perfect lens, and for years people have used a nanoscale resolution to obtain this kind of small details using near field scanning optical microscopy, which is also known as ANSOM. So, ANSOM can detect the evanescent waves which is close to the sample surface. So, ANSOM can produce images point by point by scanning. So, obviously, it is indirect and it is a slow scanning method, right. So, typically what happens, ANSOM will basically lack the versatility and the convenience compared to the far field optical systems. Also, the tip induced perturbation could limit the use in real time imaging. Then next breakthrough came when people introduced surface plasmon assistant microscopy. So, here people have used surface plasmon polariton, which are surface electron waves that can propagate at sub-wavelength scale, and using the SPP or the surface plasmon polariton dispersion at the metal dielectric interface, people try to capture the details of the sub-wavelength feature. So, here is a picture that shows plasmon microscope that is operating in the hyperlens mode. So, it is a basically gold film on glass substrate, and this is at the bottom. From the bottom you can do the laser excitation. Okay. So, you can see the plasmons are generated by the sample which is kept at the center of a hyperlens. So, it is a kind of a cylindrical hyperlens you can think of. So, you have alternating layers of metal dielectric. Okay. So, the lateral distance between the plasmonic ray, you can see it will grow with the radius, and after that when it comes out, so it basically grows. So, here it is above the diffraction limit. So, it can be captured by the regular microscope objective, right. So, that is how you can see a sub-wavelength feature from this kind of a imaging, right. So, what it is doing, it is basically utilizing the short wavelength 2D optics of the surface plasmon politons to form localized magnified images. So, a 2D mirror structure can also be formed like this. So, this is a plasmon microscope, okay, that is operating in geometrical optics mode. So, it is implemented using parabolic droplets on surface, and it is able to reflect or scatter the SPPs from surface objects to form magnified 2D image. So, you can see here that there is a nano hole array. Okay, this is the nano hole array which is illuminated by the laser excitation. So, this is the whole setup. It will have a glass prism at the bottom. So, you can send light through the glass prism that will excite surface plasmon at the metal dielectric interface. Okay. So, this is the gold film, okay, and this is the dielectric or the glass prism. Okay. So, this light basically acts as a source of the surface plasmon which is emitted in all direction. So, upon interaction with the sample that is positioned near the focal point of the parabolically, you see here of this parabolically shaped dielectric droplet. So, this is the dielectric droplet, okay, and from the reflection that is coming from the edges, okay, the plasmons basically form a magnified planar image of the sample. So, you can see here, so the image is formed here, right, and that image is basically seen by this regular microscope objective. So, the droplet edge, okay, here you can see it can act as an efficient plasmon mirror because of the total internal reflection, right. So, the image detection here is also done via far field microscope, but using the light that is scattered from the surface roughness or lithographically created structures. So, initially these hyperlens demonstrations were basically limited to 1D and focusing mainly on the UV wavelength range, as also discussed in the previous lecture. Later people made improvements, including matching the impedance, making them flat, oblate or epiradic, or even going for acoustic kind of super lenses, right. So, despite all this progress, the physical limitations remain, and typically no 2D magnification in visible spectrum is realized. Now, to overcome these limitations, okay, a novel approach called optical hyperlens has been used for super resolution imaging that would allow to overcome the current diffraction limit far beyond using hyperbolic metamaterials. Okay, you will see sphere shaped designs and new material combinations can be used for 2D magnification and also in the operation in visible range, and they can be easily integrated with the commercial confocal microscopes for real world applications. So, optical hyperlens can mark major breakthrough by using curved alternating metal dielectric multilayers to achieve strong optical anisotropy. and the whole idea here is that you need to convert high spatial frequencies, that means the sub-wavelength features, into propagating waves so that they can be captured by the regular microscope. So, the cylindrical geometry compresses the lateral wave vectors adiabatically as waves propagate radially outward, and we will see that this enables the magnification of the sub-diffraction feature into the far field viewable range. So, normally optical microscope has significantly used. So, you will see that optical microscopy is typically being used in many fields such as in microelectronics, biology and medicine, right. And conventional optical lens systems, as we know, are also limited by the diffraction limit that basically restricts the resolution. Okay. And once Pendry could predict the perfect lens, that is a concept inspired by the development of super lenses using negative refractive index material, it was possible to do sub-diffraction imaging. Okay. So, the first optical super lens was realized using silver slabs that could enhance the evanescent waves, okay, but are limited to near field kind of imaging. So, in this particular work, they have imaged objects which are slits as narrow as 40 nanometer, okay, across this silver super lens, which is also just 35 nanometer thick. So, in contrast, you can see the current optical microscopes which can only resolve objects down to around 400 nanometer. Here it was possible to detect objects which are just 40 nanometer or so. Okay. So, that was the kind of first true super resolution imaging at optical frequencies using silver super lens. So, instead of the negative refractive index material, they used silver super lens which has got a negative permittivity, right. So, this actually allowed to enhance the decaying evanescent field, and that evanescent field was having this information which was captured, right. So, techniques like near field scanning microscopy and fluorescence based imaging could bypass the diffraction limit that we have already discussed, but they sacrifice the imaging speed. So, you need lens based projection imaging, okay, to ensure that it is used for high speed applications. So, that is where artificial metamaterials can be used to overcome this particular limitation. So, plasmonics and metamaterials could offer engineered materials that have got unique properties like negative refraction and strong anisotropy. And if you make hyper lenses based on metamaterials, they can project super resolution images into the far field using magnification. So, hyper lenses are basically promising for practical usage since their first demonstration in 2007, right. So, they basically enable imaging beyond the diffraction limit. Hyper lenses are basically made of hyperbolic metamaterials, right. So, they work by projecting the super resolution information into the far field through sub wavelength magnification, and that is shown here. So, you have got an object which is sub wavelength, and then you have hyper lens which is made of hyperbolic metamaterials that will magnify the feature to a scale which can be picked up by conventional lenses, and then you can do far field imaging, right. So, higher spatial resolution basically comes from this hyperbolic dispersion law of the SPPs that enables finer details to be encoded and imaged beyond the classical diffraction limit. So, if you remember, the hyperbolic dispersion relation for SPPs will look like this: k square xy minus kz square modulus of it, okay, will be equal to epsilon d omega square by c square. Now, what is the physics behind the hyperlens. The first thing is that the light emission and scattering basically consist of two waves. One is the propagating wave that has got the low wave vectors. Typically they carry large feature information and they can reach the far field. And the other part is evanescent waves, which basically correspond to high or large wave vectors. They carry fine sub-wavelength details and typically they are not propagating in normal materials and they remain confined within the near field. Okay. So, when you look into diffraction limited imaging, that means this limitation is basically coming from the fact that evanescent waves are not able to reach the far field before they are captured. So, you are losing information. So, it means sub-wavelength details are not being contributed to the final images. So, that is why you need hyperlens, and the key requirement here will be a kind of material that supports high wave vector propagation. So, that evanescent waves coming from sub-wavelength features can be propagated, right. So, a magnification mechanism is needed to convert high wave vector waves, which are the evanescent waves, to low wave vector waves, that is the propagating waves, so that you can enable far field transmission of this kind of super resolution information. So, what is the material solution for this? The first thing is you have to understand that anisotropic plasmonic metamaterial are ideal in this kind of scenario, because they only require tuning of permittivities, not permeabilities, okay, in different directions, and that simplifies the design and also reduces the material loss. Now, the simple implementation could be they are made of alternating metal dielectric multilayers, like a kind of multilayer stack in the form of 1D periodic array that we have seen, and you have to ensure that the layer thickness is much sub-wavelength, so that effective medium theory approximation can be used to describe the directional permittivities epsilon parallel and epsilon perpendicular. Now, there are different types of dispersive metamaterials. So, if you see hyperlens, they are basically referred to metamaterials which have got hyperbolic dispersion. That means the permittivities are of opposite sign. So, epsilon parallel and epsilon perpendicular are of opposite sign, and if you use elliptical dispersion materials, they can also be used if they cover a large range of lateral wave vectors. In that case, they will also be able to pick up that large or high wave vector information from the sub-wavelength features and pass it on to low wave vector waves, that is propagating waves, so that you can pick up those information. So, the magnification mechanism is explained here. Okay. So, this is a material which has got a elliptical kind of dispersion curve. So, you can see band the flat layers into a concentric curved layers, you can get this kind of a structure. So, this can be explained by transformation optics. So, here what happens, conservation of angular momentum causes the tangential wave vectors to compress radially, right. So, these are the two cases. So, now we will see that a magnified image, which is basically a low vector image, will be formed in the outer boundary of each case, and the final image is scaled by the ratio of the boundary radii. So, what is happening? So, this is the portion where the hyperlens is placed. You can see these are the hyperlens. So, here are the sub-wavelength features, the two small features, as you can see. Okay. Now, what is the objective? You want to image it here in far field. So, this part is normally, if you consider this one, so there is no other material, you just have two sub-wavelength features, and you will see that only here you are capturing the low wave vectors. So, they are not able to resolve the two objects, right. Now, you can do that. Okay. Here assume that these two objects are separated by a distance of say 80 nanometer. So, you can either use a eccentric elliptic kind of a metamaterial, which is this one. Okay. So, in that case also you can convert this high wave vector information to a lower wave vector information like this is a high wave vector information, okay, to a lower wave vector information, and then you can come up to this boundary which can further propagate. So, here you can resolve the two objects. You can also use a hyperlens where you can clearly see that the two objects are resolvable, but not only in air. So, what is the magnification factor? The magnification factor is basically the ratio of the outer to the inner radii, right. So, that is basically tells you the magnification factor of this hyperlens. So, what is the way or method to design this kind of spherical hyperlens? So, let us look into the mathematical studies for this kind of anisotropic material design that can support light propagation from diffraction limited objects. So, the diffraction limit issue is mainly because of the loss of the evanescent waves in normal material. So, our focus here will be to see the wave propagation in isotropic and in anisotropic material that allows us to design this hyperbolic metamaterials. So, first focus on figure 6 that illustrates the field distribution of the two objects which are located arbitrarily in the xy plane and propagating along the z direction. So, the initial field distribution at z equals 0, that is in this plane, can be written as phi xyz equals 0. Okay. Now, to achieve linear propagation of these objects along z, okay. So, the field at any z position, okay, so z equals d can be written as phi xyd will be c phi xy0, right. So, to overcome the diffraction limit, the field distribution must be linearly transferred. Okay. So, that means from the object to the image plane, and it should occur without disturbance or any change in any single point, right. So, the objective here is to find or design materials that enable such linear propagation through the z direction or say in any other direction. And in this case, you can write the propagation of the electromagnetic wave will be defined or governed by this particular equation. So, that phi xyd will be integration x prime y prime phi x prime y prime 0 times integration kx ky e to the power I kx x minus x bar e to the power I ky y minus y bar e to the power I kz, which is function of x and y, kx and ky times d, okay, dkx and dky, and then finally you have this integration, that is d x bar dy bar. So, this is for the z directional propagation. So, you will see that isotropic materials have a dependency between the three wave vectors kx, ky and kz, which can be expressed via this particular equation, where you can write kz as a function of kx ky to be equal to square root of n square k naught square minus kx square minus ky square. Now, if you apply this equation to the propagation equation, this simplifies to this particular form. Okay. So, you can write phi xyd will be this integration, and then you have this phi x prime y prime at 0, that is at z equals 0, and then you have this displacement, okay, square integration over kx integration over ky, okay, e to the power I kx x minus x bar e to the power I ky y minus y bar times e to the power I alpha plus beta plus into d dkx dky dx prime dy prime. So, this particular term here e to the power I alpha plus beta d, this term is constant. Okay. So, the final equation satisfied condition for linear propagation of objects along the z direction, as you can see here. So, this equation fails to make kz independent of kx and ky, right. So, it is not like in the previous case. Okay. So, here kz is still dependent on kx and ky, and especially it is problematic when you will see kx or ky is greater than n k naught. So, as a result, what you will see, the wave becomes evanescent. Instead of propagating wave, you will get evanescent wave in the isotropic material. So, what is the solution here? You need to decouple this kz from kx and ky. That means you have to bring some strong anisotropy to do this decoupling. So, that is where you can express this as a constant. So, if you consider this value as a constant kz, so this is basically kz. Okay. If you write I alpha plus beta equals c, that is a constant, that means it is independent of kx and kz. In that case, you can write this equation as this. Okay. So, this equation can be written as phi xy d. Okay. So, the propagation along z is not going to alter your wave. Okay. So, e to the power I alpha plus beta d. Okay. And then you have double integration x prime y prime phi, this is the initial value, okay, at z equals 0, and then you have integration over kx and ky. So, this is a constant, okay, so it comes out. Okay. So, the final equation can be simply written as phi xy d equals e to the power I alpha plus beta d times phi xy 0. So, here you can see that this particular term is a constant. So, you can see that you are actually getting a linear propagation of objects along the z direction, which was mentioned in the earlier equation 2. So, suppose that we consider two nanoscale objects, for example 50 nanometer diameter holes, which are also placed 50 nanometer apart. So, these are beyond the diffraction limit, right. So, here let us see why we need the spherical geometry of hyperlens and the problem in isotropic medium with this kind of consideration. So, first thing, we are considering the medium to be isotropic such as air. Wavelength of the incident light is considered to be 410 nanometer. So, when light shines from the below, as you can see here, these are the two spherical holes or nanoscale objects, okay, circular holes you can say. These are 50 nanometer diameter and they are 50 nanometer apart. So, when light passes through the holes, you can see the field is getting diminished in the very close proximity. That means they are not able to propagate in air. Okay. The reason is that this is sub-wavelength information and 50 nanometer separation is much smaller than the diffraction limit at 410. So, typically the diffraction limit is half the wavelength. So, below this means that below 200 nanometer or 205 nanometer, you will not be able to resolve the information, and that is what we are seeing here. Okay. And this is only because that the sub-wavelength information is basically carried by high wave vector components, and these components cannot propagate in air due to their limited dispersion relation, okay, because your kx, ky and kz are interdependent. Okay, because your kx, ky and kz are interdependent in this kind of medium. So, they will not be able to support this kind of high wave vector components. So, what is the result here? You can see the light becomes a evanescent wave that cannot propagate along the z direction. So, now if you fill a hyperbolic metamaterial in the air, okay, you can see that light can propagate through the metamaterial in the z direction due to the hyperbolic dispersion, because that is where your kz can be independent of kx and ky and it can support very high wave vector. Okay. So, this is where you can see the hyperbolic metamaterial being present and light is propagating along this direction. This is again air. So, this is where it basically stops propagating, right. So, these are important observation that as soon as the light exits from the hyperbolic metamaterial, it again decays exponentially and you cannot see this further. So, this decay basically limits the detection of sub-diffraction images at the image plane. So, here they are able to propagate, but then as soon as they exit, you are not able to capture it, because the sub-wavelength information is basically getting exponentially decayed. So, what do you want? You want to also spatially separate out this information, so that you can do far field imaging. So, that is the current challenge remains is that you need a practical far field imaging to be done for this kind of super resolution application. That is where you can take help of this spherical geometry, So, you consider a half sphere shaped hyperbolic metamaterial. So, you are having this alternating layers of metal dielectric, but increasing radius. So, this hyperbolic metamaterial will basically enable the light propagation along radial direction, okay, which are supported by large in plane wave vectors. So, these are like below diffraction limit, but as they propagate, okay, they basically get spread out. So, you can actually now get this information above the diffraction limit, which can now couple to the far field, and you can get that imaging done. Okay. So, this is where the spherical geometry can provide this gradual magnification along the in plane direction, right. So, here you see the schematic of a spherical super lens, which comprises of 9 pair of silver and titanium oxide layers, and in this particular figure you see sub-diffraction limited objects which are propagating in the radial direction r with gradual magnification along the plane direction, in plane direction, that is phi and theta. So, as a result, the objects which were actually below diffraction limit, they were now magnified beyond the diffraction limit at the outer boundary of this material, and at the boundary between the metamaterial and the background of the glass, they can be now detected by conventional microscope because they are above the diffraction limit, and that is how you can do the imaging. So, the main working principle of this kind of hyperlens is that it magnifies sub wavelength, or you can say sub diffraction limited objects, and projects them to the far field without diffraction. Here you can see what is happening. This is the detailed cross section of the hyperlens of half sphere shaped multi-layer stack. So, you have a chromium material which has got this small information. Okay. So, this is the information that is diffraction limited. There is a slit, then you have this metal dielectric layer, alternating layers. Okay. Here you can see carefully, so that it marks your k theta, this is k r, and k phi is going into the screen. Okay. So, this particular figure tells you that you have got a sub-wavelength image that is curved on this chromium layer, and then you have this metal dielectric oxide multi-layer hyperlens. Okay. The transverse magnetic component of the unpolarized light relative to the plane is basically labeled as k, okay, that you see here. So, what happens in position A? It is basically a sub diffraction scale object which are supported by large in plane wave vector k theta and k phi. Okay. So, you are having this one large k vector. So, this is the corresponding position in the isofrequency contour. Okay. So, this is the hyperbolic metamaterials contours, and then you are basically allowing to start this radial propagation. Okay. Because this hyperbolic metamaterial and they support this large wave vector, so evanescent waves can propagate. So, they are propagating and they are coming to a position B, which is here. Okay. So, at this position what is happening, that your k theta and k phi are gradually compressed along this hyperbolic curve as your radial position is constantly increasing, right. So, this is because the optical momentum, which is k in cross r, okay, is basically conserved at every point. Now, with the radius being increased, you will see that the in plane momentum, which is k in, is basically decreasing. Okay. So, that is why it is going down the slope. Okay. And at point C, the distance between the 2 points become large enough, okay, or you can say the 2 objects become large enough, so that they are no longer diffraction limited. So, in this case the light will be now supported by the diffraction relation of normal material, that is the glass substrate. So, you can see if you take this as the isofrequency point of glass. So, here you can have this phase matching or momentum matching. So, light can now propagate into free space after exiting from this particular point at C. Okay. So, this is where you see the light can escape into free space after exiting the hyperbolic metamaterial. So, this is how it works. So, you are initially in position A, then you are moving through this point, that is your B, and then when you are coming out of this metamaterial, okay, and you can match the momentum of free space waves, you can couple to the free space wave and you can be detected directly. So, in this case the sub-wavelength information can be captured as a magnified image, which can be detected by a conventional microscope. So, with that we conclude this lecture. If you have got any query regarding this lecture, you can drop an email to this particular email address mentioning the course title and the lecture number in the subject line. Thank you.